This week we're going to look at groundwater recharge, and in particular how we can use caves as observatories of the groundwater recharge process. There's two parts to the presentation. This part is part one. We'll ask the question, groundwater recharge, what is it? And we'll go on to consider why we might want to use caves as observatories of groundwater recharge. And that will conclude with a virtual tour of Wellington Caves in the central west of New South Wales. And the picture on the right hand side is from that cave, showing some data loggers that are recording the water that's percolating through the cave from the ceiling down to the floor, and which are just above the groundwater level, above the water table. In part two, which is the next presentation, we'll consider how we might want to model karst hydrology and the water movement from the surface to the subsurface, and I'll give a case study of both observations and modelling from the Macleay region of the mid-north coast of New South Wales. And both of these presentations directly align with the assignment, which is going to be one where I'm going to ask you to look at the groundwater recharge at Wellington Caves in New South Wales and analyse that data and model it as well. Let's start with the question, recharge, what is it? And recharge is the replenishment of the groundwater. However, its definition and the terminology can be confusing. For example, it can be defined by the source of the water that's generating the recharge. You'll see rainfall recharge used, which is when the recharge occurs from rainfall infiltrating through the soil, and then down to the groundwater and the groundwater table. But there's also recharge from rivers and from lakes, where these have water leaking from them. So if they're a losing river or a losing lake and they're situated above the groundwater level, then water will leak from those features into the groundwater and recharge it. So that's a definition by source, but the recharge can also be defined by process. And here in bold, I have two of the terms. We could have focused recharge and we can have diffuse recharge. The focused recharge is from a specific point location. So that could be from leaking rivers, leaking lakes. It could be sinkholes or fractures. Diffuse recharge is used when recharge is from a non-point source, and typically that would be through the soil, right? So that recharge is through a larger area. And then we can further subdivide focused recharge into localized recharge, which could be a specific point. So that could be a fracture or a sinkhole on the Earth's surface that water will flow through. And it could be indirect recharge. So that's from losing rivers and lakes where the water is leaking from the bottom of them, but over a larger area. So it's a bit less focused and it's more indirect. You now have some definitions of recharge, but how does it occur? The example on the right-hand side shows the example of recharge occurring on a soil and vegetated surface. And to have recharge to occur, then you need an input. You need rainfall or precipitation, which is this term P, and that has to be greater than the losses of water from the soil, which is from evaporation or transpiration, which is combined as evapotranspiration, ET on this figure here. And if P is greater than ET, water will accumulate in the soil, and when the soil reaches its fill capacity, the point when it can hold no more water, then it can start to lose water. And this may occur from runoff over the surface, so that's the R term here, or you might get what is called deep drainage or drainage down to the groundwater level, which is this term D here. A useful concept is this term called the zero flux plane, and this is also drawn on this figure, so it's the dotted line here and also on the left hand side here. And this is the depth below the land surface, where below that location the water can actually move down towards the water table. So above this line you would lose water to the surface due to transpiration and evaporation, but below that line you're beyond the zone where you might actually have tree roots going to depth and actually taking the water and having it for tree water use. But at a certain depth they can't access that water anymore. You're beyond the zone where evaporation can occur and you get downward water movement. And the zero flux plane can be anywhere between 1 and 30 meters below the surface, and recharge only occurs when the water has actually reached the water table. So this is this term here, R. As it's migrating down towards this water table, it's termed potential recharge. It can potentially form recharge. So far, you have considered the definitions of groundwater recharge and the process of groundwater recharge. But how do we actually measure it? And because it's a subsurface process, it's actually very hard to measure. The first technique I'm going to introduce you to is the method of chloride mass balance. And this is an arid zone diffuse recharge measurement. It only works in water limited environments where salts can accumulate in the soil zone over time due to high evaporation, and then occasionally when there's recharge events they get flushed into the subsurface, into the groundwater. This is a reliably used and cheap method for recharge estimation, and it works well because chloride is very soluble. You know that from the previous lectures, from the sodium chloride example. Salt is highly soluble in water, including groundwater and soil water. Chloride is also conservative. It doesn't take place with many other chemical reactions, so the chloride that will be present in the soil will not be affected by any other process by the time it gets flushed down to the groundwater, and it's not substantially used by vegetation. So it's a very good tracer. So the method works like this. If you have dry conditions for long periods of time, you get lots of evaporation and evapotranspiration in the soil. The salts will accumulate in the soil and you'll have a high chloride value in the soil. When you get a recharge event and the soil field capacity is reached, water will be flushed into the subsurface and hopefully will reach the groundwater table as recharge, and that will carry a signal of some of that salt from the soil. If there's regular recharge events over time, you'll get less chloride in the signal relative to the amount of water. If you have low amounts of recharge, you'll have a predominance of the chloride signal. So there's a simple method and there's a nice simple equation here. So the recharge in millimeters per year is the amount of precipitation measured on the surface in millimeters per year plus the ratio of the amount of chloride measured in the precipitation, because that's the ultimate input term, you need to know what that is, compares the amount of chloride present in the groundwater. And there are some assumptions of this method. It assumes there's no other chloride sources. The only chloride source is from the rainfall input that then gets stored in the soil zone as salt. It assumes that chloride is conservative, which is a reasonable assumption, and it also assumes that all rainfall generates recharge, so that rainfall is the only recharge source and there's no other sources of recharge. So if there was a leaking river or lake, that would have a different chloride concentration and this technique wouldn't work. Let's look at an example to help explain that better. The example is from Rottnest Island. This is from the research of Eliza Bryan, who's a former UNSWB's undergraduate and postgraduate researcher, now working as an environmental consultant. That's a picture of her sampling one of the boreholes on Rottnest. So here we have some data. We have the rainfall chloride concentration, which we measured in the units of just under 2 millimoles per litre. We have the borehole chloride concentration, which ranges between 4.24 to 9.24 millimoles per litre. And we can just take the ratio of those two values then to work out of the percentage of rainfall recharge. And if you take the lowest value from the boreholes, that would suggest that 46% of the rainfall is recharged to the aquifer. If you take the highest value, it suggests only 21% of the rainfall is recharged. The recent average rainfall on Rock Nest Island is 597 millimeters per year, which means that we can calculate annual recharge, which ranges from 125 millimeters to 274 millimeters in a year. So you can see the advantages of the chloride method. It's very simple to work out a recharge estimate, but it's an annual estimate only. It doesn't get any higher resolution, and there's a large range of values there. There's a lot of uncertainty. A second method that's used to quantify recharge is the water table fluctuation method, amusingly abbreviated to WTF. This is a higher resolution technique. It requires you to have high resolution water table measurements through a water level logger. But if you have continuous measurements of water level, and you can see the groundwater level rising and falling over time, a bit like this example here on the top right, where we see a decline in water table. So it's getting deeper under the Earth's surface. So this is depth from the surface. The water table starts off at about 3.7 meters below surface and goes down to about 4 meters below surface. Then there's a recharge event, and the water level recovers and then goes down again. And we can measure the height that the groundwater has gone up, and we can make some assumptions about the properties of the rock and how much water leaves the rock. Then we can turn that height of water that's been recharged into a recharge estimate. So the equation, this equation here, the amount of recharge is related to the change in height over time, which is this on the right hand side, multiplied by something called the specific yield. And the specific yield is the porosity of the rock minus the specific retention, which is the amount of water that it actually loses over time. Think of something like a sponge which has got pores in it. You fill that sponge with the recharged water, but there's going to be water draining out of the bottom of the sponge at the same time. And you have to account for both how much water can be stored in the sponge and how much is leaking at the bottom to work out the specific yield. And if you know what that is, then you can work out the recharge from the recharge event. So this is best applied to shallow groundwater systems with rapid water level changes, where you actually get a recharge event, a bit like this one in the top right hand corner. If you go to deeper groundwater systems, probably that recharge event will be smoothed out as the water gets mixed with other waters from different parts of the surface. The limitations are that the water has to arrive faster than it's leaving to actually get the groundwater table to rise. That isn't always the case. And this specific yield term needs to be measured or known, and it's very hard to measure. So typically researchers will use a lookup table. Here's a lookup table here for different classifications of gravels, and you just plug this value in, but that increases the uncertainty. I recommend the text by Healy and Cook from 2002 as a classic if you want to really know all the details about the water table fluctuation method. The advantage is you can get recharge at the scale of individual recharge events, but there's a large uncertainty because the specific yield is rarely known precisely, and it doesn't always record recharge events. I'm going to finish this part about recharge by looking at this really messy figure, which is a huge comparison of all these field methods of measuring recharge, just to give you an example of how messy the data is and how well we understand how much rainfall is needed to recharge groundwater. And we can take almost any one of these figures. I will take one at random. I'll take this one here, which is carbonates. So you can see here, this is the average recharge that has been estimated by one of these techniques. And you can see it's on a log scale, and it's in millimeters per year. And this is for Australia. So you can see here that the recharge estimates vary from between about 1 millimeter per year recharge through to about 800 millimeters per year. And on the x-axis, the horizontal axis, is the average rainfall in millimeters per year. This is not on a log scale, so this goes from 0 to 3000 millimeters, and most of the data here is in the range of 0 to 1500 millimeters. So this suggests that in carbonate regions, maybe a maximum of 1/3 to 1/2 of all the rainfall is recharged. But you can see there's huge uncertainty in this data set, and you can see lots of data points that are all the same color on a single line, which probably come from a single research database. It's a really messy data set. It's annual average yet again. It doesn't really tell us enough about how much rainfall is really needed to recharge groundwater at an individual event scale. Why use caves or other underground spaces as observatories or groundwater recharge? Hopefully I've demonstrated that the analysis of water chemistry or water level fluctuations in boreholes, they can't tell you how the water got into the borehole. You don't know if it's come from the soil adjacent to the borehole, or it could have travelled from some distance from a nearby leaking river or lake. And the water table fluctuation methods and the chloride mass balance method, and also a water isotope method that I haven't described earlier, they can't differentiate the recharge pathway. And they're often of very low temporal resolution, annual estimates. If you go into the subsurface, a cave or a tunnel or mine, you can actually directly observe the water percolating from the surface to the groundwater table. You know where the water has come from because that's what's above the cave or the subsurface feature that you're in, and probably it's through the soil and possibly as a focused recharge through sinkholes or closed depressions. What you're measuring isn't recharge, you're observing potential recharge. So that's the water that's moving towards the water table, and you don't actually know if it will actually form recharge yet. And so that depends on where you are in the cave or subsurface space compared to the groundwater table and the zero flux plane. You want to be closer to the groundwater table than the zero flux plane. And if you can see a drip water hydrograph response in a cave after a rainfall event, so a bit like the water table fluctuation method for boreholes, then you can compare it directly to antecedent rainfall amount, and you can calculate a rainfall recharge threshold. So you can work out how much rainfall is actually needed to generate groundwater recharge at that location. Let's take a virtual cave tour, and we're going to Cathedral Cave, which is at Wellington Caves in the central west of New South Wales. And the cave that we're going to have a virtual tour into is the same one that you're going to be working on in your assignment. In the tour, we'll start down near the cave's kiosk and we'll walk up the hill, up a path to the cave entrance, which is somewhere around about there. And then in the subsurface, you will see the cave tour, which goes something like that. And then we come back onto the surface, you'll look at the surface vegetation. Hope you enjoy the tour.